Hi, everyone. I am Ancy and I'm a research fellow at the University of Birmingham. And first of all, thanks for the opportunity to share this recent work on chasing granulation on a quiet K-dwarf HD166620. Jen, you said it right. And this project has been shaped by the efforts of some truly amazing collaborators, particularly from the HARPS-N consortium. And it wouldn't have been come together in this shape without them. And I would take this opportunity to thank all of them. Let's slowly sneak in. As we all know, an Earth-like planet orbiting a Sun-like star induces a reflex radial velocity wobble of around 9 centimeters per second over the course of a year. And to measure the precise masses and orbits of such potentially habitable planets around nearby F, G, and K-type stars, we need extremely precise RV measurements or EPRV measurements with precision better than 10 centimeters per second with stability over several years. Sorry. Over the years, with the help of precision radial velocity measurements, we have been able to consistently get below 1 meter per second precision, particularly in the past 3 to 5 years. And however, these efforts are seemingly capped at around 50 centimeters per second, a level comparable to granulation-induced radial velocity variations. But now, with the new generation EPRV instruments stepping onto the scene, including Espresso, Express, Maroon X, and Noid, we would, in theory, be able to push the RV precision closer to the targeted 10 centimeters per second precision. However, fine-tuning these instruments and making the most of their available data is an essential step towards detecting true Earth analogs orbiting nearby stars. And the key piece of the puzzle here to reach the goal of the 10 centimeters per second precision is to understand the additional spurious signals in the EPRV data from these state-of-the-art spectrographs. As we are aware, the major source of these additional signals are instrumental systematics and various stellar variability phenomena, which complicates the detection of small exoplanet signals. And in this talk, we will discuss both the instrumental systematics and the small stellar variability-induced variations. Talking about stellar variability, I know I don't have any deeper insights into these processes than the audience here. However, I included this slide as it is customary to begin with an introduction slide to stellar variability. I'm not going to spend much time on this because you all know what these are. And in this talk, I'll be focusing on granulation, which is a stochastic process that happens on relatively shorter timescales, ranging from minutes to several hours, and capable of inducing radial velocity variations of the order of centimeter per second, a couple of centimeters per second to up to 1 meter per second in main sequence stars. As we are now at the 10 of the tide with the current EPRV spectrographs and soon with the HARPS-3, providing sub-meter per second RV precision required to extract the 10 centimeter per second RV signal of an Earth analog, the challenge of granulation and supergranulation has intensified. And as we are aware, granulation is a convective phenomena involving the hot plasma upflowing through the brighter granules, which cools down and downflow through the dark intergranular lanes. And as the bright granules outscale the darker intergranular lanes, both in the size and brightness, this entire phenomenon of granulation will introduce a net convective blue shift. And as we know, it is crucial to understand the observable radial velocity signatures of this phenomena to inform the existing granulation models and to devise mitigation methods to facilitate the detection of Earth analogs. So we carried out a pilot study to characterize granulation on a quiet K-dwarf HD166620 using HARPS-N. And why we chose HD166620? So this star was carefully chosen for this study due to some characteristic stellar properties. HD166620 is a bright K2 type star, less massive and cooler than our sun. And HARPS-N has been observing this star for the past 13 years as a standard star and also as part of the Rocky Planet Search or the RPS program. And we did a deep planet search in the 13 years of HARPS-N data and found no significant planet signals down to 60 centimeter per second level. And most importantly, the chromospheric activity index of this star has been recorded for more than 5 decades as part of the Mount Wilson survey, as you see here in blue. And what you see here is the S-index, and you see this beautiful 17 years magnetic activity cycle, which seemingly have flattened out in early 2000s and entered a prolonged activity minimum since then. And as I said before, HARPS-N has 13 years of data for the star. And this 13 years of HARPS-N data shown here in red confirms that the star continues to be in the same prolonged activity minimum state, making this the only known Maunder minimum analog. And to put in context, Maunder minimum is the period where our sun went through a prolonged activity minimum phase for around 70 years in early 1700s, where the number of active regions recorded was less than 50 for the entire 70 years period, in contrast to the tens of thousands of sunspots otherwise. So, in the absence of the strong magnetic activity in this star, we expected granulation to be a dominant contributor to the observable RV variability. So we observed HD166620 intensively for 2 continuous nights using HARPS-N and Express in June 2024. And we took back-to-back 180-second exposures to capture the short minute timescale of granulation while averaging out the PMODs. And in total, we obtained 290 HARPS-N observations over 2 nights. And to our surprise, the seeing was exceptionally good during the majority of observations on an average of 0.4 to 0.6 arc seconds. And the contemporaneous express time yielded 64 observations on the first night. The rest of the first night and the entirety of the second night was lost due to smoke at the telescope site. And here is the data. And the black points here show the HARPS-N observations. The red points show the express observations, showing fair agreement in the 1.5 hours of overlap. All good so far, but not quite. We see large intra-night variations, particularly in the second night. There is a 2 meter per second peak-to-peak RV variation observed. And this amplitude is considerably greater than the anticipated granulation signal on a quiet K-dwarf. So we looked into any possible instrumental systematics. And after an extensive search, we traced these variations back to the 2 good seeing we had on the nights of observations. So we looked at the ratio of the total counts recorded by the 2D Echelle spectra with the integrated count recorded by the exposure meter. And what you see here in blue is that ratio recorded by the CCD and the exposure meter. And in pink, what you see is the signal to noise, the ratio between the signal to noise at the order of 60 and 30. You can see that these 2 measures show nice correlations. And here, and the coefficient of this correlation is around 0.9 for both the nights. And this obvious U pattern that we see here is mainly the air mass, but the residuals of the air mass with the ratios shows that the air mass alone cannot explain all the structure that we see as we see in the steps here. So we investigated, so there's something more than the air mass that is playing the things here. So we investigated the possibility of any seeing related instability that could result in the fiber injection instability. So as I mentioned, the recorded average seeing was around 0.4 to 0.64 much of both nights, which is considerably smaller than the fiber entrance aperture. And if we suppose the sharp seeing could cause small variations in the directions of the focal direction or the focal ratio of the beam emerging from the fiber, the illumination of the collimator would change. And this would affect the total flux reaching the CCD and also its spatial distribution. And the consequent changes in the relative weightings of the photon counts in different areas of the detector will result in spurious RV measurements. I know it's complicated but yeah, this is what is happening. And to correct for this, we extracted the RVs from different parts of the detector as the photon counts have difference in relative weightings in different parts of the detector. So we extracted RVs from different parts of the detector to develop a decorrelation metric, thanks to Andrew Cameron, who devised this method. On the left here is the density plot showing the relative flux variations in the 16 subregions on the detector used to characterize this CCD illumination variation. And on the right, in blue, you see the HARPS-N RVs versus the Julian date obtained from the data reduction pipeline. And we used the singular value decomposition, or SVD, to isolate this illumination-induced RV variations. And in orange, now you see the projected DRS HARPS-N RVs to this SVD representation of the illumination variations arising from this fiber injection instability. Now, in green, as green RVs, we see the residuals. Basically, it is blue minus orange, which should now contain just the astrophysical signal and the photon noise. And for the remaining analysis, where we look for the granulation signals, we used these instrument-corrected green RVs. So that is a momentary pause for the instrumental saga. Let's get back to the major science goal of the telescope proposal, which was to search for the granulation signal. And this is how we carried out the analysis. We used the line formation temperature information to investigate the manifestation of granulation signal on different parts of the spectra. I'll go through these step by step so that we will be on the same page. So first, we got the temperature spectra from the flex spectra. Following Almola et al. 2022 and 2023, we used the RV code, which makes use of the spectral synthesis using pi-SME, which is spectroscopy made easy, to estimate the formation temperature of each spectral lines. And this was done by estimating the stellar temperature below which at least 50% of the emergent flux originates at each wavelength point. And this rainbow plot here shows a normalized synthetic flux spectra for HD166620, color-coded with the estimated formation temperature. Here is the zoomed-in wavelength window of the previous rainbow plot that I showed. Here you see the formation temperature assignment better. And according to Almola 2022, the formation temperature can be used as a proxy to arrange the spectral lines with the altitude in the atmosphere that it is formed. So we used formation temperature as a preferred variable for probing different photospheric height and types of activity occurring at various heights. For context, here, the blue segments showing the cooler parts are formed at the top layers of the photosphere or of that stellar atmosphere, while the hot segments are formed in the deeper layers. And if we now segment the spectra based on the temperature information and extract radial velocity from these segments, we can investigate the sensitivity of different depths to granulation effects. So that is the basic idea. And to extract the RVs, we used the CCF method, the cross correlation function method, and we followed this roadmap. First, we selected the most appropriate line mask. Since HD166620 is a K2 star, we chose the espresso K2 mask for cross correlation, and here it is. And we now have to construct temperature sensitive CCF line masks to extract temperature sensitive RVs. To do that, we estimated the wavelength bounds for each line by cross-matching with the line list from RV. And we then defined the flux gradient weighted temperature for each line within the defined wavelength bounds. And this will ensure putting more weights on the wings, which contain more RV information than the cores. And we then partitioned the K2 mask based on the estimated formation temperatures. Here, red lines are used as the hot mask, and blue lines are used as the cold mask to extract the cold RBs. And we then cross-correlated the entire spectra using these segmented masks to extract temperature-sensitive sensitive CCFs for each temperature regions. So here we chose two distinct temperature regions which are balanced to contain equal RV content and equal RV, to have equal RV variance. And as usual, we then fitted Gaussians to these CCFs to measure the RV time series for the 290 epochs. Now, the question is, do we see granulation in the data that we have? To do that, we used a one-component aperiodic Gaussian process model following O'Sullivan and Egbrine 2024. And this model fits granulation and supergranulation signals as random processes, and it uses Gaussian processes to isolate multi-component signals corresponding to different stellar activity processes. In this case, as we are interested in the granulation signal, given the specifically designed observations, we preferred a one-component granulation aperiodic model. And here are the results. This, thanks to Neve for the extensive analysis that she did as part of this project. And this corner plot here shows the GP posteriors made for the entire data. There is no temperature splitting here. In this corner plot, we have the characteristic granulation timescale, the standard deviation, and the noise measure here. We found no significant detection of supergranulation, but that was no surprise given the limited observation baseline we have, which is insufficient for constraining supergranulation. And here, the blue crosshairs represent the predicted values for granulation variations for HD166620 from the scaling relations as in Besu and Chaplin 2017. And we see well-constrained granulation signals with a characteristic timescale of around 43 minutes and a standard deviation of around 20 centimeter per second. And these results are from the entire spectra, as I said. Now, what about the cold and hot segments? Can we detect granulation from the segmented spectra? So that is our next question. Here, the red shows the hot RVs, and the blue shows the RVs from the cooler temperature bins extracted using the CCF method. And on a closer watch, you can also see the blue crosshairs here, and you can see that the cooler RVs agrees better with the predicted values. And the hotter bins seemingly have a higher amplitude and is seemingly dominated by the window function of the data. So that's what we are seeing here. So based on the results, we observe slightly better detectability in the cooler temperature bins. That means from the shallower layers in the stellar atmosphere. And this somewhat contradicts the conventional understanding based on the convection model and the solar observations. Based on the conventional understanding, we know that granulation-induced variations affect the weaker lines more. And these weak lines are formed in deeper layers at higher temperatures. So we expect granulation variations to be more pronounced in the hotter bins or the redder sections. But we find slightly better detection in the cooler bins in contrast. We couldn't yet establish a strong reason behind it, but we do have put forth some feasible postulates in the paper, like it might be due to the dominating window function in the hotter RVs. But yeah, that is the postulate that we put forth. I think that brings me to my conclusion slide. To conclude, HD166620 with its very low log R prime HK measurements and confirmed grand activity minimum phase will be an ideal test bed to devise techniques to push our detection limits and to learn more about our instruments. And the very important finding from our study was the newly found instrumental systematics rooted from the fiber injection instabilities, which gave rise to RV variations of a couple of meters per second since most of the EPRV spectrographs, to my knowledge, share similar fiber specifications, I would like to emphasize that these instrumental effects would not be simply specific to HARPS North. So we have to be careful about these instrumental systematics when we are looking for these small scale variations on our way to detect Earth-like exoplanets. And in this study, after addressing these instrumental variations, we detected granulation signals with characteristic timescales of under an hour and with a amplitude of around 20 centimeter per second. And we also found that granulation-induced variations are slightly better detectable in the RVs extracted from the cooler regions of the spectra formed at the upper layers of the stellar atmosphere. To complete or to get better understanding and to validate this result, we need more data, and it is too expensive to ask for because we need continuous observation, continuous shorter exposures. So we need to extend the study to more main sequence stars to devise adequate mitigation methods to minimize the effects of granulation. So those all are the major highlights, and I'm open to any questions, and many thanks for listening.
Hey, thank you very much, Anna. Questions from the audience? I see Drake's hand is already up, so go for it, Drake.
So do you see any effects with the granulation signal with the overall wavelength? At the shortest wavelengths, I would think granulation contrast, the temperature contrast in granulation would be greater than at the longest wavelengths. So your granulation signal would be stronger at the short wavelengths. Did you look for that?
Actually, the spectral cut is actually made in flex and not in wavelength, so we don't have any. But in this, so if I go back to the temperature spectra here, so the larger wavelengths, so the temperature cut made here is based on the temperatures. Sorry, the flux actually in the flux and not in the wavelength. So I don't have any clear answer for how it is varied across wavelengths, but I think Andrew Cameron, after looking into some Muram simulations, it seemingly has some major variations in the radar, if I'm not mistaken. So you see more.
Yeah, I did a few experiments a while back, splitting the spectrum into a blue half and a red half, and there is some difference. However, the star for which I did that was an active one, so it's not clear whether I was seeing granulation or activity signatures. But certainly there does seem to be a wavelength dependence in all forms of non-planetary goings-on that you see in stellar spectra.
Okay, thank you.
Thank you.
Other questions from the audience? I'll ask one while people ponder for a moment. So apologies if I missed this, Anna, but when you showed the K2 mask that you're using and then the selection of which lines go into which temperature bin, it looks like there are a few lines that are still in gray here, so they were not selected. And I was just curious what caused them to be left out of the analysis. Are they outside of your temperature bins or disregarded for another reason?
So this one, the illustrated one here, misses some temperature regions here. Okay. So this is, I've actually forgot to update this figure here, but in the paper, this is updated. So if you look at the temperature bins here, there is a region from 4,337 to 4,486 is missing here.
Okay, so, yeah, so these just fall in the middle.
That's a good catch. I forgot to update this figure.
Drake, is that a second question or a residual hand?
That's just, I forgot to lower my hand. I'll do it right now.
Not a problem. And then Anna, so I know that this was kind of a Herculean effort of getting multiple full nights of observations on HARPS North. Do you have, I know that's an expensive way to do things, but are there efforts underway already via observing proposals that are going to try and do this for more stars, or is that a future effort?
So that is currently in the pipeline, but we don't know what will happen because it's very telescope expensive. We don't know.
Yeah. Okay, potential TAC members. Pay attention.
Yeah, it's important.
Eric,
Please give
yeah.
time.
Eric, I see your hand up. Go right ahead.
Did you experiment with trying to allow for like jointly fitting a GP to the oscillations simultaneously with the granulation signal? Or is the data just not able to constrain that at all?
So actually, for these observations, the exposure time was set for 180 seconds to actually mitigate the effects of oscillations. So we didn't expect oscillations to be very dominant.
So that will certainly help suppress them, but I mean, sometimes you get like these annoying, like beat patterns or something of the oscillations, and so even if you've suppressed them dramatically, I could imagine there's some residual degeneracy between your granulation model and the pulsation. So be interesting to explore to what extent that's a concern and to what extent it's just paranoia.
Yeah, at the moment we haven't tried that yet, but yeah. So we tried to mitigate the effects during the observations itself, we actually didn't go that way. Yeah.
Thanks.
But again, for the timescales that we see here, we didn't see much. Yeah, but that's a good avenue to look for. Yeah. Thank you, Eric.
Okay, any other questions for Anna from the audience? Okay, well, if not, let's say thank you for an excellent presentation. We'll be posting this to our archive as per usual, and we'll be back next month with our May iteration of the Colloquium, still sorting out speakers for that. I hear that the abstract sorting for EPRV 6 is coming along nicely, and so there should be results out next week for plenary talk selection. So look forward to that via email if you are intending on going. Oh, and if you're planning on attending EPRV 6, we are going to organize a post-conference extra research collaboration day on Friday, July 4th. And so I encourage any of you to attend. The current idea is to split that between networking efforts in the morning to help increase connections between people in different research groups and different research areas, and then spend the afternoon. I think it'll be split between collaborative research proposals. So if people want to think about telescope or grant proposals that would benefit from involvement from a variety of research teams or expertise, we'll have a group working on that. And then another group working on developing community resources. So things to help people who are either new to the field as a whole or new to specific areas of EPRV, so that you can get spun up a little bit faster and have useful tutorial notebooks and things like this to help you learn how to work with different types of data or different types of analyses. So more info about all of that will be going out soon, but as you're making your travel plans for Porto, keep it in mind and come hang out on Friday if you are able. Okay, with that, I think that is everything for today. So thank you all for calling in, and we will catch you next month. Take care in the meantime, folks. Bye.
Thank you.
Right. Bye, everyone.